Now we continue our discussion of the Burrows-Wheeler transform and the FM index. In the previous video, we saw the Burrows-Wheeler transform and we answered the questions of why it's useful for compression and why it's reversible. And now we're going to talk about how you can use it as an index. So there's a data structure called the FM index, which is basically the Burrows-Wheeler transform, but with a few auxiliary data structures, which we'll cover in this lecture. So the FM index is really the BWT, which I'm showing here. Again, the BWT is the last column of the Burrows-Wheeler matrix, plus some other data structures, which we'll discuss. But the core of it is just basically the F and L columns, the first and last columns from the Burrows-Wheeler matrix. Like we said before, the last column is the Burrows-Wheeler transformed string, and the first column is really simple, right? Because the whole matrix is sorted alphabetically, this first column is always going to have this very simple structure where it's just a $sign followed by a chunk of whatever the first character is alphabetically, and then whatever the second character is alphabetically, etc. So this F column can really just be represented with an array of integers, one per alphabet character. And like we said last time, the Burrows-Wheeler transform yields a string that's more compressible. We showed that it yields a string that brings like characters together into runs. So if we wanted to, we could compress L. And so when you think about how much space we're taking, if we're just storing L, and then we're storing a very compact representation of F, and we're storing some other auxiliary data structures, which are relatively small, that seems really good. After all, L here is just exactly the same size as T. L is the Burrows-Wheeler transform of T is just a permutation of the characters in T, so it's the same size as T. So if we're talking about DNA strings, this is very heartening because we can store a DNA string in very little memory. Right? If each nucleotide is taking 2 bits, we can store an array of 2-bit nucleotides, and this Burrows-Wheeler transform string is a same size array of 2-bit nucleotides. That's not very big. So like, for example, the human genome, which is about 3 gigabases long, 3 billion nucleotides long, that fits in a 2-bit per base array that weighs in at under 1 gigabyte. So the core of this index is something that's surprisingly small, especially when you compare it to the suffix array, which, like we said, is at least 12 gigabytes and maybe more, or the suffix tree, which by doing some extrapolation we said is something on the order of 47 gigabytes or so. So this has the potential to be very small compared to those other data structures, but first we have to discuss what these auxiliary structures we're adding are. Okay, so the Burrows-Wheeler matrix is related to the suffix array, like we said before. Basically, when we sort the rotations of the Burrows-Wheeler matrix, we get an ordering that's exactly the same as if we had sorted them by suffix. Again, because once you hit a $sign, the tie is broken, and so it doesn't matter that there are characters to the right of the $signs in each of these rows of the Burrows-Wheeler matrix. It's essentially the same as sorting the suffixes. So this order and this order are exactly the same. But again, in our index representation, we're storing the last column, which is the Burrows-Wheeler transformed string, and we're storing the first column, but we don't have all this stuff in the middle. That stuff is completely thrown out. So whereas when we had the suffix array, we could query that using binary search, because we had these strings, right? Because we kept T around, and these are offsets into T. So we could do the character comparisons to drive our binary search when we had the suffix array index. But we don't have that here. We don't have T. We don't have these middle columns from the Burrows-Wheeler matrix. So binary search is not a possibility here. We need another way of using this data structure to enable searching within T. So overall, our strategy is going to be to look for rows of the Burrows-Wheeler matrix that have P, our pattern, as a prefix. So this is similar to what we did with the suffix array. We used binary search to find the range of rows in the suffix array that had our query, our pattern, as a prefix. We're going to do a similar thing, but we're going to do it in a different way. So first of all, using the suffix array, when we tried to find the rows that had p as a prefix, it involved matching prefixes of p to prefixes of suffixes in the suffix array. So it's as though we were matching p in a left to right direction. But we're going to do the opposite now. We're going to match successively longer suffixes of p. So we'll start with the shortest non-empty suffix of p, which is just the letter a. And we're going to find the range of rows in the Burrows-Wheeler matrix that have a as a prefix. And then from there, we're going to try to when we make our next step, we're going to try to find the range of Burrows-Wheeler matrix rows that begin with BA, the next longer suffix. And then in the next step, we'll try to find all the rows that begin with ABA, at which point we're done. We've done something very similar to if we had been using the suffix array and left to right matching to match p against the index. Okay, so now let's start at the very beginning. How do we find the range of Burrows-Wheeler matrix rows that begin with A, that have A as a prefix? That's easy. Again, because F is so simple, the structure of F is so simple, to find all the rows that begin with A, well, we know we have to skip over the $ to get to the first A, and then we skip down another number of rows equal to the number of A's in the text, which we've already counted up. And so that gives us this range right here. Basically, it's the entire block of A's in the first column. Okay, great. So that's the first step. Now the next step is to refine that, is to start with that range, and now calculate a new range, which is the range of rows that begin with BA. So how do we do that? So here's the range we found already. That's the range of rows that begin with A. Let's look over here now in the last column at those same 4 rows. And we see some revealing stuff. So for example, here are 2 B's. And we can see their ranks. We wrote down their ranks using the B ranking. These are not B's, they're not quite so relevant, but these 2 here are B's. And B's are what we're looking for because we're trying to match the next longer suffix of P, which is BA. And wherever we see a B in the final column, corresponding to an A in the first column, that means we found an instance where B preceded an A in the text. In other words, we found an occurrence of BA in the text. So we're looking in these rows, and we're noticing these B's. But we don't just notice that there are B's or that there are 2 B's. We can see their ranks. They're of ranks 0 and 1, which means that these occurrences of BA correspond to wherever we see B0, the B of rank 0 and the B of rank 1 in the first column. So that's how we'll get our next range. We want the next range to include B sub 0 and B sub 1. Okay, so here's that range right down here. And again, it's very easy for us to use the LF mapping to get from seeing that B sub 0 is here to knowing exactly which row begins with B sub 0, and same for B sub 1. So this is our new range, and that's the range we were looking for. That's the range of rows that begin with BA, the next longer suffix of P. Now, of course, we want to find the next longer suffix, which is ABA. So we do something very similar. Again, here's our range of all the rows that begin with BA. We look in the last column. We see A's here. That's what we're looking for. These are instances where BA is preceded by A, and that's what we're looking for. And furthermore, we see that the 2 instances correspond to the A of rank 2 and the A of rank 3. So we can use the LF mapping to calculate a new range, a range that includes the A of rank 2 and the A of rank 3 in the first column. Here we go. And finally, that is the range of the Burrows-Wheeler matrix, of the range of rows in the Burrows-Wheeler matrix that have ABA as a prefix. So that's what we were trying to do. This is the same range, the same beginning and end, that we would have found if we'd used the suffix array in the analogous way that we use the suffix array doing binary search. We would have found the range of elements from 3 up to 5 exclusive. That's the same range we found here in the Burrows-Wheeler matrix, but using the Burrows-Wheeler transform and the LF mapping, not using binary search. And furthermore, we were matching progressively longer suffixes of P in this regime, whereas over here we were matching progressively longer prefixes of P. Now, one thing that contrasts our current situation with the Burrows-Wheeler matrix, with the way we would do things with the suffix array, is that the suffix array also tells us where these occurrences are in T, right? Because that's what the array is telling us. We found the rows that have ABA as a prefix. The suffixes for which those are the prefixes are the ones that offset 0 and 3. We just read that directly off from the suffix array if we're using the suffix array. Over here, we have no such information. We do not know. We know that we found 2 matches, right, because of the size of the range that we got at the end of that procedure, but we don't know where those matches are. So that's a problem. We'll have to solve that later. So that was a scenario where the pattern was a pattern that did occur in T. Let's just see briefly what happens when we have a pattern that doesn't actually occur in T. So here's the new pattern, BBA. And I've already done the procedure that I showed you before in order to find the range of rows that have BA as a prefix. Here they are. And now we want to find the range of rows that have BBA as a prefix. Well, again, we go look in the final column and see what characters there are in those rows. And there's no B's. So that tells us there are no instances where BA is preceded by a B, which tells us that P doesn't occur in T. So that's how we know. If we get to this sort of point and we realize the next character we'd like to match does not occur in any of these rows in the last column, that's how we know that the pattern does not occur in T. Now there's the question of how exactly do we go about looking in the last column for the characters that we're looking for, right? So for example, I showed you the example where we matched A. We found the range of rows that have A as a prefix. Then we wanted to find the range of rows that have BA as a prefix. And so we looked in the last column and we found these 2 B's. Well, what exactly do we mean when we say we're looking in this last column and searching for these 2 B's? Do we mean that we are literally scanning it character by character so that we're examining every character, every final character of each of these rows? That seems potentially like a bad way of doing things because we can potentially have a very long range where we're doing this scan in the last row. In fact, the range in a worst case could be as long or almost as long as the Burrows-Wheeler transform string here. So we could have an amount of scanning to do that's essentially linear in the length of the Burrows-Wheeler transform string, and we don't want that. We would like whatever we do in order to locate the relevant B's here to be very fast. So this is another problem we have to fix. We've left ourselves now 3 different problems that we have to fix in order to make this efficient. One of them is what we just discussed, which is that we have to figure out how we would really do this scan so that we don't, in the worst case, have to do a scan that's linear in the length of the text. We still have this problem where we're storing ranks, and the array of ranks is a length M array, which makes the index data structure way too big. It's actually at least as big as the suffix array, and we certainly want to be smaller than the suffix array. And then once we get this final range, where now we know the range of Burrows-Wheeler matrix rows that have our pattern as a prefix, we need to know where those matches actually occur in T. In the suffix array regime, that was easy because the suffix array just told us. But now we don't have the suffix array, so how do we figure out where these matches actually are with respect to T? So let's take this first question first, the question of how are we going to do this scan quickly and figure out which B's, if any, are here in the last column for the range of rows that we're considering. All right. So is there a really fast way we could do this? Is there, for example, a constant time way that we could determine which B's and how many B's are here in the last column of these rows? Well, one idea is we can pre-calculate a lot of stuff in order to allow this to be constant time. And so what I'm going to propose is up to every single position in the Burrows-Wheeler transform here, we're going to pre-calculate the number of A's and the number of B's, the number of each letter of the alphabet. It's just A and B in this case, but for every letter in the alphabet, we're going to calculate up to every position in the Burrows-Wheeler transform how many times we've seen that letter occur, up to and including that row. So in this instance, that tally might look like this. Here's our tally matrix. So up until this row, we're looking only at the Burrows. We're looking only here for our tally. We're ignoring F. We're looking at L. So up until this row, we've seen 1A and 0 B's. So we put a 1 here and a 0 here. Up until this row, we've now seen 1A and 1B. So we put 1 and 1. And now we've seen 1A and 2 B's, 1 and 2, 2 A's and 2 B's, 2 and 2. So you can see what this matrix is encoding. Now there's lots of information in this matrix. We'll address that later. But you can see how this matrix can allow us to do what we wanted to do, but with just a couple of lookups in the matrix. So for example, say these are the rows we're interested in. We'd now like to know, are there any B's here, and what are their ranks? So we can determine that by looking in two cells of this tally matrix. First of all, this cell here, the cell for the row just above the range that we're looking at. Because there are 0 B's up to and including that row, what that tells us is if there are any B's down here, the first one's going to be the B of rank 0, because there haven't been any B's up to and including the previous row. So we know that now. And when we look in this cell and we see a 2, we can see that because the difference between 2 and 0 is 2, we can see that there were 2 B's in that range. So in these 4 rows, there were 2 B's. We can infer that because the difference between the value in this cell and the value in this cell is 2. So we know that there are 2, and now we know their ranks. Their ranks B sub 0 and B sub 1. And we did all that, we inferred all that just by doing 2 lookups in this lookup table, a constant amount of work. So that's quick, but it takes a whole lot of space. It's constant time, but it requires that we store this entire dense matrix, which is of size, number of positions in the Burrows-Wheeler transform times number of characters in the alphabet. So let's cut down on that space usage a little bit. Here's another idea. It's very similar. We're again going to pre-calculate the number of A's and B's, the number of occurrences of every character in our alphabet, up to not every row, but just some of the rows. We're going to pick some of them. Let's say we pick every 5th row, for example. And we're going to calculate that same tally as before, but only up to those rows, right? So again, we are going to tally up to this very first row. Again, we've only seen 1A, so this is 1 and this is 0. Then we're not going to store any such tallies for these rows. But we are going to for this row, because we said every 5th row. And up to this point, we've seen 3 A's and 2 B's, so we put a 3 and a 2. So now, we're not taking up as much space. We're taking up about 1/5 the space. But we want to do that same pair of lookups we did before. We'd like to look in this cell, and luckily we've stored this cell. This cell is one of the ones that we actually filled in. But now we want to look at this cell, and we have not filled that cell in. So what do? So we have filled it in this cell. So while we don't have this cell, we do have this cell. And so from the value here, and the fact that this character is an A, we can infer that this must also be 2 here, right? What value goes here? Well, that's a 2, and that's an A, so that must have been a 2 before. We can also, by the way, since this is a 3 and that's an A, we can infer that this was a 2. So just by looking at the values in this row and the character here, we can figure out what are the values in the row before. So even though we didn't store the values in this row, we can infer them, and we don't have to go too far afield to figure out what are the values that belonged here. We just had to sort of go to the nearest checkpoint. So again, to resolve a lookup for a character C in a non-checkpoint row, like here, we're just going to keep scanning along L until we get to the nearest checkpoint. We'll use the tally at that checkpoint, but we'll adjust it according to the number of occurrences of that character we saw along the way from here to get to the nearest checkpoint. Let's see another example. So let's say we're in this row. We'd like to determine the rank of this A. This is similar to what we were doing before. It's a somewhat simpler question. We just want to know what is the rank of this A. And we have our tally matrix, but again, it's not dense. We haven't stored every value. We've just stored some rows for this tally matrix. So we have a tally up to this row, and we have a tally up to this row, but we've not explicitly stored tallies up to these grayed out rows here. But we still want to know the rank of this A. So the way we would calculate it, again, is we would walk to the nearest checkpoint. In this case, the nearest checkpoint is this one above. It may not have been, right? It could have been that the nearest checkpoint was below, like we saw on the previous slide. But in this example, the nearest checkpoint is up here. It's above. So we would walk to that checkpoint, looking at characters of L as we go, right? Noticing that along the way we found these two A's. And now we find that the tally in this cell is 482, and we'd like to know the rank of that A. So we're going to adjust this 482 by adding 2 to it, since we saw 2 A's along the way, and so those are 2 additional A's that we would encounter on our way to this cell. So we have to add 2. And to turn it from a tally into a rank, we're going to adjust it by subtracting 1. That's going to make it 0-based so that it works as a rank, the way we've been ranking the characters. So the rank of this A, if we were to write in a rank right here, we would put 483. Alright, now how about this B here? We'd like to know the rank for that B. We can do the same thing. We can start in this row, and we can walk to the nearest checkpoint. In this case, we're now closer to this checkpoint down here, so we're going to walk down. We're going to go boom, 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 boom. We saw 2 B's along the way to get to this cell here. This cell says 439. In other words, up to and including this B, there were 439 B's. So to calculate the rank for this B, we're going to subtract 2 for the 2 B's we saw along the way, and we're going to subtract another 1 to turn it from a tally into a rank. So we're going to do 439 minus 2 minus 1. So this is the B of rank 436 right here. So you can see how we can resolve ranks, and we can solve that same that problem I presented before of trying to figure out how many characters occur within a certain range in the Burrows-Wheeler transform string. We can do both those things by using these tallies, and we don't have to store every value in this tally matrix. We can make this. We can store only some of the rows, store tallies only for some of the rows, and that's sufficient. Now, if we really wanted to improve the bound, we said that in the worst case before we were using the tally matrix, looking at all the characters in the Burrows-Wheeler transform matrix that correspond to some range, that could be, in the worst case, order m time. If we were to store these checkpoints some constant distance away from each other, so if we were to just pick a number that we would consider a small constant, like 30, say, and then store these every 30 rows, then the amount of work that we have to do to recover the rank of any character or recover the value of any cell of the tally matrix, even the ones we didn't store, that would still be constant work, because we'd have to walk some number of cells to get to the nearest checkpoint, but it's never going to be worse than whatever the inter-checkpoint distance is. And then we're just going to do some constant number of additions or subtractions in order to adjust that number according to the way we need to adjust it to get back our rank. So if we store those checkpoints, this checkpoint, if we store these a constant distance apart throughout the entire tally array, then we're guaranteeing that the things we described on the previous slide and on this slide are constant time. It might be a fair amount of work, right? Whatever that quote small constant is, it could be 100 or 1,000 if we wanted it to be. Those aren't very small, but they're still constant, so we still have a guarantee on how much work we have to do in order to resolve one of these ranks. So there's clearly a trade-off here. If we make the checkpoints further apart, we're incurring less space. We don't have to use as much space to store those checkpoints. On the other hand, we might have to travel a long distance to walk to the nearest checkpoint to resolve one of these rank or tally queries. If we store them closer together, we use more space, but we do less work to resolve these rank or tally queries. But we did, in fact, solve 2 of the 3 problems on that previous slide. We can solve this problem now. We can now figure out how many bees and which bees, in other words, which ranks do they have, here, just by doing a couple of lookups in that tally matrix. And even if the cells aren't explicitly stored in the tally matrix, we have a constant time way of walking to the nearest checkpoint to resolve our query. So with checkpoints, this is now constant time. Before, we also were concerned that we were storing the ranks for every row. Basically, we were storing something like the tally matrix for every row. But that same checkpoint idea that we used to make this constant time, even without storing the entire tally matrix, is exactly the same trick that we can use so that we don't have to store the entire ranks array here. We can solve both those problems by storing periodic checkpoints that hold how many times each alphabet character occurs up to regular intervals in the Burrows-Wheeler transform. Okay, we still have that third problem. We need to be able to figure out, once we have found the range of Burrows-Wheeler matrix rows that have our query as a prefix, that have P as a prefix, we still need to figure out where those occurrences are within T. Otherwise, we can't really use this data structure for all the same things that we were using the suffix tree and the suffix array for. So how do we know where these occurrences are with respect to T? One naive solution to this problem is we can just store it. We can just pre-calculate it for all possible rows. In other words, we can store the suffix array. That's exactly what that is. So if we just kept the suffix array alongside our Burrows-Wheeler transform string here, and we did the procedure we did before in order to find the range of Burrows-Wheeler matrix rows that had P as a prefix, well, we can just look in the corresponding elements of the suffix array, and that tells us where those 2 instances of ABA occur within T. They occur at offsets 0 and 3. Right? You can sort of tell. Here's T right here. They occur at offsets 0 and 3. But that, of course, is naive. That's keeping a lot of keeping m integers around in our index, which makes it obviously at least as big as the suffix array, and in fact bigger because we had to store some other stuff over here too. So we'd rather not do that. Let's do something less naive than that, but still of the same spirit. So the idea, sort of like our checkpoint idea before, is we're going to store some, but not all, of the elements of the suffix array. We will store some of them, but not all of them. And here I'm showing you a suffix array that is sort of lined up parallel to this Burrows-Wheeler transformed string here. But not all the values are filled in. Some of them are grayed out, indicating that those are suffix array elements that we did not keep in our index. But we kept some of them. So these we kept. Okay, so we'd like to know now the offsets within T of these 2 occurrences of ABA, and we have this available. So this bottom one, this row, we can just do a lookup, and we happen to keep that value. So we know that that occurrence of ABA occurs at offset 0 within T. Great. Now for this row, we do not have that value in the suffix array. So that lookup failed. We discarded that entry. So how do we get it back? We can use the LF mapping. In other words, even though that element is not filled in, we can figure out that this is the A of rank 1, right? This is A sub 1. We can use that partial, we can use our checkpoints and our partial tally matrix to figure that out. which means that we know we can immediately jump to the row that has the A of rank 1 in the first column, this row here. And in doing so, we've jumped one character to the left with respect to t. So we're looking for where this ABA occurs with respect to t. Now, by doing this, using the LF mapping to jump to this row, we're now in a row that corresponds to one character to the left of where the ABA occurs. You can see that in my figure here. Here's the ABA. But now we're in the row that begins with the character just before that ABA. But now this row does have a element of the suffix array stored that corresponds to it. So we know that this AABA occurs at offset 2 within the text t, which means that ABA occurred at offset 3. So we were looking for the offset of this occurrence of ABA. We hadn't stored it. We didn't have that element of the suffix array. So we jumped to the left by one character within t, and that rotation, that suffix, we figured out was at offset 2. So if we started at one position and jumped to the left and ended up at position 2, that must have meant that we started at position 3. So we can do a little calculation like this. So again, if we keep some elements of the suffix array but not all, but the elements that we keep in the suffix array are spaced a constant distance apart, then this invocation of the LF mapping is something we'll have to do only a maximum of a constant number of times. There's a very important issue here. I'm saying that if the values that we save of the suffix array are a constant number of positions apart with respect to t, so that's different from saying with respect to the suffix array. In other words, I'm not just keeping every 32nd element of the suffix array. That doesn't quite work with the guarantee that we're looking for. What I'm saying instead is that for every 32nd suffix of t, take the longest suffix and then take the suffix that's 32 characters shorter and the next suffix that's 32 characters shorter, etc. We would store each of those in the suffix array, but not the others. So as you can see in my diagram here, I've stored every other element with respect to t, but it doesn't quite turn out to be every other element with respect to the suffix array. You can see there's one here, none here, one here, none here, and then there's 2 in a row. But you can see that the numbers in those cells are a constant distance apart. 0 and then 2 and then 4 and then 6. That's an important point. We're saving the suffix array values that are a constant number of positions apart with respect to t. So there we go. We solved that third problem now. So at the expense of having to keep some values of the suffix array around, right? So, and it's still an order m number of integers we're keeping because we're keeping every constant number of suffix array elements. At the expense of keeping some of them around, we'll call this the suffix array sample, we now have the ability to figure out where any particular occurrence of our pattern is in a constant amount of time. We have to do a constant number of LF mappings to get to an offset within t for which we've stored the suffix array element. We've stored that rotation or that suffix's offset within t. Okay, so now let's analyze how big the thing is. After all the various data structures we discussed, how big is this thing, this FM index? So what do we store? First of all, we have to store F, the first column, but as we said, we can store F just by storing basically the number of times each alphabet character occurs. We might pre-process that a little bit more so that we can very quickly jump over entire chunks of that first column. Then the last column is the Burrows-Wheeler transform itself, so it's a permutation of t, and we're going to keep that. So we're going to store those m characters, not m integers, but m characters, right? It's just a permutation of t, so it's the same size as t. We have to store our suffix array sample. So let's say that we took 1 in every 32 rows or something like that. Then this A here would be 1/32. and m is the length of t. So we have to store that many integers. And then for the checkpoints, again, we're going to have this fraction b. So let's say we kept a checkpoint for every 128th row, for example, of the Burrows-Wheeler matrix. Then this would be 1 over 128 right here. And for each checkpoint, we have to store an integer for each character of the alphabet. So this is m times this fraction, that's the number of rows for which we're storing a checkpoint, times cardinality of sigma, which is the number of characters in the alphabet, that many integers. So for a real-world example where we're indexing the human genome, and we pick this A and this B, we can plug in all those numbers and we can figure out that the total size of the entire data structure, everything included, first column, last column, suffix array sample, and checkpoints, total size is going to be around 1.5 gigabytes, which compares very favorably to the suffix array, for example, which was 12 gigabytes without pre-calculated LCPs, and then more if we had pre-calculated LCPs. Or compared to the suffix tree, which when we extrapolated from how big the Mummer index was, we said was probably going to be around 47 gigabytes or so. So this is very, very, very small compared to those two data structures. So small you can easily fit in the memory of a laptop for sure. So this is the paper that first described the FM index. I need to say that the version that I described in these lectures is a very simplified version of what's in the paper. I simplified the description and then also the bounds so that the bounds could be, first of all, more consistent with how we described the suffix tree and suffix array, but also much simpler than what are described in the paper. The paper has much more complicated bounds, in part because they're trying to the space bound is being they're trying particularly hard to optimize that. Also, one thing we didn't discuss, but that we only really hinted at, is the fact that that Burrows-Wheeler transform string, the last column of the Burrows-Wheeler matrix, is compressible, and so we actually have the option of compressing it as part of the index, so that that contribution toward the total size of the index can be squeezed down and made much smaller. We would then have to go about decompressing it, perhaps selectively, decompressing pieces of it when it comes time to query the index. But that is possible to do, and that's another thing that's discussed in the paper that we didn't discuss here.